A student performs an experiment to determine the concentration of hypochlorous acid. They've given you the Ka value. It's 3.5 by 10 to the minus 8. That is your clue in the exam that it's a weak acid, which means if you write any equations with hypochlorous acid, it's going to have a double arrow or a reversible arrow in it. The student starts with 25 mils of the acid in a conical flask and titrates it against 1.47 molar NaOH, sodium hydroxide. The equivalence point is reached after the addition of 34.23 mils of NaOH, and luckily for you, they've actually given you the equation. HOCl plus NaOH turns into NaOCl plus H2O. Part A is only 2 marks. You can use the marks of the question to gauge how much you're supposed to freak out by. Okay, it's a 2 mark question. It should be relatively straightforward. So if you notice yourself overthinking, writing so many steps, chances are we need to wheel that back. Yeah. 2 marks goes to calculating the concentration of HOCl. Ignore part B. The question is given to you in order for a reason. If part B scares you because it's 5 marks, we're gonna ignore that for now. Yeah. Part A is your standard titration question. You've got 25 mils of the acid in the conical flask, and in the burette, you've got 1.47 molar NaOH, and you added 34.23 mils of it. This is your standard direct titration question. If the question is asking you for the concentration of HOCl, that means you want to end up at HOCl, so we should start with the NaOH instead. If you're going to relate chemicals via an equation, it has to be done in terms of moles. So when we say start with NaOH, we're saying start with the moles of NaOH. C times V. 1.47 molar by 34.23 mils is 0.03423 liters. What do you get for the moles of NaOH, please? Point oh 0.0476721. Thank you. You guys, I'm getting different answers. 0.050318. The equation is given to you in the question. It's a 1-to-1 ratio with the HOCl and NaOH, which means your moles of the acid is the same. So moles of HOCl is moles of NaOH is 0.050318. And then now that you're at the chemical in question, the question asks you about HCl. We've now got the moles of HOCl. We just go straight to concentration. Your equation for concentration is N over V, 0.050318 mole. And then now, whenever you're subbing in numbers into an equation, it has to be for the same chemical. So if you want the concentration of HOCl, you sub in the moles of HOCl, you sub in the volume of HOCl, which isn't the 34 that we've already used, it's the 25 now. So 0.025 liters for your denominator. What do you get for concentration? 2.0127 molar, and then the 25.00 mils is 4 sig figs. The 34.23 mils is 4 sig figs. The smallest sig fig you used is the 1.47 molar for the NaOH. So that's 3 sig figs. We round off to 2.01 molar if we want the full 2 marks. Okay. So part A is a straightforward, direct titration question. What we're not used to is part B. Part B has asked you to determine the pH of the solution in the conical flask after the addition of 28.55 mils of NaOH. Do not let the wording of the question confuse you. The fact that it's a titration is actually irrelevant. The fact that it's in a conical flask is actually irrelevant. They're not asking you a question about prac skills, yeah? This part B, all it is a mixing acid and base question. Okay, part B is just mixing acids and bases. All right, now what you've done in part A is you use stoichiometric ratio in part A. We could do that because 34.23 mils is at the equivalence point. By definition, the equivalence point is when you've reached the stoichiometric ratio. Yeah. So the 34.23 mils, you're allowed to do ratio work for. That's why we did 1:1. But here in part B, they've wheeled it back. They didn't ask you for pH at the equivalence point. They asked you for it at 28.55, which is actually before the 34, which actually means this is before you finish the titration. Yeah. So guys, part B, if you reword it, this is what part B literally is. Part B is you've mixed HOCl, 25 mils of it, and now we know the concentration, 2.01 molar. You've mixed it with 1.47 molar NaOH, 28.55 mils of that. What's the pH of that mixture? That's all part B is. Yeah. So take part B out of the titration context now. All right. Again, if you want the pH of a mixture, think about what you're mixing. You're mixing an acid with a base. The chemicals are going to react. So therefore, the pH of the mixture is going to depend on what's even still existing in the mixture when that acid-base reaction is done. Yeah. If you want to know what's left over once the reaction's done, you need to consider what you even put into the mixture in the first place. Yeah. You put in some of the acid and then you put in some of the base. The equation has been given to you in the question, so I'll just take this and move it down here, just so that we have all your working out in a nice spot. For me to know what's left over to affect pH, I need to know what I added in the first place. My moles of HOCl, C times V. Now you guys might be like, now hold on, how am I supposed to know how many moles is in the 28.55 mils? Guys, you calculated the concentration in part A, yeah, which is why the question is structured that way. They had to treat it like a standard titration question first, and then ask you about this random volume after. Yeah. Now, part B came from part A. I know we've rounded it to 2.01. It's the last number in your calculator though, so just press answer. I'm going to take this. Okay, I'm only rounding off to present my answer. When I keep on going, I take it before it rounded off. So 2.0127 molar times new new volume. Sorry, the volume of the acid is the 25. The 28.55 is for the base. So for the acid, it's the 25. 0.025 liters. What's the moles of the acid? 0.050318. And then the moles of the base, again, this is now a mixing acid base question. Yeah, I'm not doing stoichiometry work yet. This is the moles of the acid and base that I put in the first place. They told me it's 28.55 mils. That's what they want. Yeah. So C times V, concentration of the base was 1.47 molar. And then the new volume that they want me to mix in is 28.55. So 0.02855 liters. What is the moles of NaOH? 0.04196 mole. Thank you. These are the moles that I added Just because I've added it into my mixture doesn't mean they all affect pH. What affects pH at the end of the day is what's still left over after the reaction's done. Yeah. So step number 3, if I want to figure out what's left over, what's in excess, I can do a process of elimination. I can identify the limiting reagent first. If A is the limiting reagent, B is the one that's in excess to affect pH. Yeah. When you're doing the limiting reagent, you take the moles, you divide it by the coefficient in the equation. In this case, the coefficients are both 1, right? The equation was given to us. So for HOCl, 0.050318 divided by 1, same thing. For NaOH, 0.04196 divided by 1, same thing, 0.04196. Your limiting reagent is the smaller number out of the two that you get. 0.05 for the HOCl is bigger than 0.04 for the NaOH. 0.04 is smaller. So therefore, NaOH is my limiting reagent. We're only calculating the limiting reagent as a stepping stone to get to what's in excess. The NaOH goes away. It's not going to affect pH at the end of the day. What's in excess is the HOCl. That affects pH. However, just because you put in 0.05 moles of HOCl doesn't mean the entire 0.05 affects pH, because even though it's left over, some of it still gets reacted. So you're not concerned with how much you added, you're concerned with how much is left over. So the moles of HOCl that still exists once the reaction's done, that's still left over, depends on how much you added in the first place minus how much did get reacted, did go away. So from step 2, you know that you added in 0.050318 minus the amount reacted with the limiting reagent. The limiting reagent is NaOH. We've figured that out by now. And the ratio with HOCl is 1 to 1. So if 1 mole of NaOH reacted, 1 mole of HOCl reacted. If 5 moles of NaOH reacted, 5 moles of HOCl reacted. The amount of NaOH that actually reacted is 0.04196. So therefore, your amount of HOCl reacted is the same. It's a 1 to 1 ratio. Now, guys, you're popping in both numbers into this line of working out. Yeah, 0.05 minus 0.04. You need to go, if you haven't stored the number, you need to go back to get it. Okay, these questions about mixing acids and bases you've seen already have multiple steps. Your rounding off errors will get bigger. Yeah, so if you haven't, if you didn't save the number before, go back to get it, because we need both numbers without any rounding. Yeah. What is the moles of HOCl left over that actually affects pH? 0.0083496 mole. Thank you. That's the amount that will actually affect pH at the end of the day. However, if we quickly recall your pH equation, pH doesn't take in moles, pH takes in concentration. So this is the moles left over, that's fine and good. I'm going to convert it to a concentration now. 0.00839496. At this point in the question, I've mixed my acid and base together. So that when I divide it by the volume, it's going to be the total volume of the mixture. It was 25 mils of the acid and 28.55 mils of the base. The total volume is 0.025 plus 0.02855 liters. What is the concentration of the leftover HOCl in the entire mixture? That does affect your pH. Point 15592. Thank you. When we record, not record RECALL, record. When we record the pH equation earlier, negative log base 10 of concentration, it was a good thing that we converted it to concentration. But then the other thing to keep in mind is even though we've got the correct variable now, concentration, we don't have the correct chemical. It's H plus concentration, not HOCl concentration. Yeah. So I need to figure out how much H plus actually comes out of my HOCl. I do that via a chemical equation, and it's the acid dissociation equation. If it's a strong acid, you use a single arrow. However, the question gave you the clue earlier. It has a Ka of 3.5 by 10 to the minus 8. You will only have a K value defined if it's weak. So in this case, I'm going to set up a double arrow, OCl minus, aqueous plus H3O plus. Because it's weak, I can't use stoichiometric ratio straight away. Just because it's 0.155 of acid doesn't mean it's 0.155 of protons. I have to set up an ice table. So I'm starting off with that 0.15592. This is probably a good point to save your numbers in the calculator, yeah? Because now that we start to fill out the ice table, there's going to be a few numbers coming in, okay? We start off with that 0.5592 molar of your HOCl. The water we don't have to worry about because it's a pure liquid. It won't go into your equilibrium expression anyway. At this point in the question, there hasn't been any H3O plus. There hasn't been any protons yet. So the initial concentration of the protons is 0. But you guys know now, with these kinds of questions, is the concentration of this one 0? No, it's not. Okay, when you're doing acid dissociation, it normally is 0 because this is the only reaction in the question, yeah? However, this time with this question that I'm doing, this is actually the second equation I've written in my entire working out. My first equation was up here. Okay? So you guys are telling me it's no, OCl minus concentration isn't 0. Where else do you see it? In what formula in this equation? In the NOCl formula, there's some OCl here. So you're used to subbing in the concentration of both products in an ice table as 0. That's because you normally start with it. Yeah? That's because that's normally the first reaction in the question, and none of the products have been made yet. However, in this case, this is the second equation you've written. The first one was up here, and here there's some OCl. OCl was the product of the first reaction. The amount of product depends on the limiting reagent. We identified in the steps above, before we even made the ice table, that the limiting reagent is the NaOH, and this was the amount of the limiting reagent, about 0.04196 of it. And if it's a 1-to-1 ratio, the amount of NOCl, the amount of OCl that we're looking for, is the same. It's a 1-to-1 ratio. 0.04196 moles of your NOCl, 0.04196 of your OCl minus as well. Okay? That's the moles though. Your ice table doesn't take moles, your ice table takes concentration. So we are going to have to segue out this way just a little bit. Your moles of OCl minus is your moles of NOCl, is the 0.04196. That's the moles of the limiting reagent, NaOH. The reason we're doing this is so that we can fill out your ice table, which doesn't take moles, it takes concentration. So I'm going to sub it in here. Again, this is the total volume. So that's the 0.025 plus the 0.02855. If you didn't store this number, again, you're going to have to go back to get it, yeah? The errors in rounding off will multiply. You don't want to round anything off until the end. What's the concentration of the OCl minus? 0.78372. molar. And then that's going to go into my ice table. If you get a nice fraction, I don't think you do. These numbers are a little bit ugly. If you happen to get a nice fraction, though, writing it in the fraction would probably make your working out a bit nicer, yeah? But at the moment, my ice table is not looking very pretty. 0.78372. Because you're storing so many numbers, be careful to label what letter you stored it as so that you don't accidentally get the wrong number out, yeah? There's still 1 0 on the right, so according to Le Chatelier's principle, I'm still shifting to the right and away from the left. My E row is filled out. I can sub it into my equilibrium expression, Ka. 8372. Again, keep everything in your calculator. Plus x with another x on 0.15592 minus x. If you're solving for x, k should be given, otherwise it's not possible to solve for it mathematically. They gave it to you at the very start of the question. It was 3.5 by 10 to the minus 8. If you imagine it in your head, when you expand the brackets, you end up with a quadratic. Yeah, so it's going to take a lot of work to solve for it. I'm going to do a simplifying assumption. Ka is very small. And again, we're not assuming that x is 0 or x is negligible full stop. If we assume x is negligible full stop, this x goes away. If you assume x is negligible, then there's no x to solve for, which is what we're trying to solve for. So we don't assume x is negligible. We assume x is negligible. Keep on going with the sentence. X is negligible relative to whatever number it's with, which in this case happens to be two numbers. X is way smaller than the 0.78. X is way smaller than the 0.15592. So then I can cancel the x's in here out, which still leaves me this x that I can solve for. I can't lose all of my x's. It doesn't make sense. So this approximately becomes 0.78372 with an x on 0.15592, and that's still equal to your 3.5 by 10 to the minus 8. All right, so I know filling in the ice table takes a lot of work. That's true. However, when you get to this point, x is actually easier to solve for than in your other questions. Yeah, multiply your denominator over. Divide your numerator. If you get confused with your stored numbers, check it quickly before you pop it into this. Yeah, check that you've got the 0.155 and the 0.78. What do you get for x? 6.96 times 10 to the minus 9 molar. Thank you, because x is a concentration that came out of the ice table, so it's molar. And then we don't actually want a random letter x, we want the H plus or the hydronium concentration. So if you go back to check, the hydronium concentration is the x, which is exactly what we want. So now you can sub it straight into the pH equation. So pH is negative log base 10, H plus or H3O plus, same thing. And what do you get for pH? 8.1571. Okay. And then you round off to the Ka in the question's only 2 sig figs. That did affect our working out. So we round off to 2. You end up with 8.2 to 2 sig figs. All right. So that's your working out done, but hopefully I can't end it here because there's now a big elephant in the room. What's the issue with our answer? It's above seven, even though what? That's not the issue. You have to combine it with something else. It's above seven, and what's the issue with it being above seven? It's above seven, even though we've got an acid in excess. Exactly. Okay. So you've got a few different explanations for this. The only reason we use pH of 7 as the dividing line is at what temperature? It's at 25 degrees Celsius, yeah? So when we say oh a pH of 7 is neutral and a pH less than 7 is acidic, that's at 25 degrees Celsius. So it's okay for you to get a pH above 7 for an acid. It probably means that it's at a different temperature. Yeah. The temperature was not specified for us in this question. Okay, so we don't know. What you can do if you really wanted to, you could take this number, go search it up on a data sheet online. If the information's even available, search up, oh, the Ka of hypochlorous acid at 25 degrees Celsius. And then if you do get 3.5 by 10 to the minus 8, then we have an issue. Yeah, but it's probably not at 25. Um, because otherwise you're right. If it was at 25 and it's the acid in excess, you should get it below 7. Other option is there's an issue with the question. Okay. But that is your answer.